So hello and welcome everyone to this webinar. Thank you for setting aside the time to be with us here. I'm Johannes from DHI in Australia. Today our webinar topic is Assessing Flood Dynamics in Rivers and Riparian Wetlands, an Integrated Hydrological Approach. Our presenter today is Dr. Michael Brian Butts, Senior Hydrologist and R&D Program Manager for Water Resources at DHI in Denmark. Michael has more than 25 years of professional experience in hydrology. His experience includes hydrological and geophysical fieldwork, hydrological data analysis, network design, and application of hydrological databases. He has both developed and applied integrated surface and groundwater models for water resources, flooding, urban hydrology, eco-hydrology, and water quality management applications. He has managed, designed, and delivered novel decision support tools within flood forecasting, nitrate management, climate change and adaptation, and water resource planning. He has also been an external lecturer in catchment modeling at UNESCO IHE since 2001. All over to you, Michael. Thank you.
Thank you, sir. And listen, thanks for the introduction, and thanks everyone for joining this webinar. I hope I can make it interesting for you and worth your while. So I'd like to use two quite different examples to talk about modeling of riparian wetlands, and the first one is local, so let's go straight there. And of course, this is technologically challenging again. There we go. So this is a collaboration between ourselves and the University of Copenhagen, the University of Aarhus, and the Danish Geological Survey. And they've provided all of the lab and field data that we've used for the modeling here. And the background for this is, as I'm sure you all know, that these riparian wetlands have a number of really useful functions. And I've listed a few of them here. Of course, recreation and scenic beauty. They provide a series of habitats for encouraging biodiversity. They can be used to retain floods and even move them around. And then they can also retain sediment and nutrients. And one of the big drivers here in Denmark in terms of the ecological status is, of course, the Water Framework Directive. And within that, the European countries have to produce these action plans for their catchments. And in Denmark, which is a fairly intensive agricultural country, then it's the restoration of the rivers and floodplains for reducing nutrient loads. That's one of the main aims of these plans. And for example, there's a goal to transform about 16,000 hectares of current farmland to wetlands. And what we think is interesting about this is what we're trying to do is put together, link together surface water flooding, the unsaturated zone flow problems, groundwater subsurface flow, and also put this together with the nutrient processes. And what we'd like to focus on in particular is looking at what processes are controlling the flow, what processes are controlling the nitrate retention, and how can we tackle this and model this in an integrated way. So this is the case study. You're looking at the top left at Denmark. It consists of the Jutland Peninsula on the left, the island of New Zealand on the right, and in the middle, the island of Fyn. And that's where the case study is, shown in the black square. And if you look at the map, zoomed in map, you can see there's a dark line going through the middle here. This is the old watercourse, or the watercourse that was introduced back in the 50s, I believe, where this area was drained for farming. And then the open line that you can see in the middle here is the current watercourse, and as you can see, it's been restored. There have been meanders reintroduced into the river system. And those meanders were actually taken from aerial photographs and then basically reintroduced as they were from those photographs. The cross sections have been raised and narrowed, and there's a lot of so-called tile drains in Denmark. So when the groundwater levels rise, then these drain into the river, and they've been either disconnected or moved. For the modeling work, we have been using this combination, Mike Shee, which is a hydrological model. And as I've shown here on the left, then we can use that, of course, to model water levels and fluxes and so forth. It also can model advection dispersion processes, so we can model the transport of conservative substances. And there are a few water quality processes within MikeShe, relatively simple descriptions. But we have another tool called Mike Ecolab. It's a kind of ecological modeling calculator, if you like. And we can use that to model things like indicators, just combinations of different variables, including model variables. We can look at chemical reactions, which is what I'm going to talk about today, but you can also use it in kind of an agent-based modeling approach where you can look at species and individuals in a agent-based framework. Before we started this work, of course, we then had to integrate these two models and make sure that everything's working as it should, and we've done some verification studies. This is one of them. This is just a simple groundwater case where we have decays in 3 species, and those 3 species could be nitrate to ammonia, or if it's organic chemicals, could be PCE to TCE and then DCE. And you can see our comparison here with the MikeShe Ecolab model and the analytical solution here. And then we have, then we have some unsaturated zone experiments here. These are column experiments, and we're looking at the transport of bromide as a conservative tracer, and then the transport of a pesticide, in this case isoproterone, in these unsaturated zone experiments. So that's the verification. And then in terms of the wetland and the nitrate processes there, we have a relatively simple description, and this is meant to be practical rather than academic. And I have to admit, this is not my key area of expertise, but if you look very carefully at this, you can see that in the overland component, in the unsaturated zone, and in the saturated zone outside of the wetland, then we have a relatively simple 2-step process from nitrification to denitrification. Then within the wetland, we have this peat saturated zone area where we actually have introduced a number of different processes, including a very simple plant growth model. And there are some things we're leaving out. We're not looking at what's happening in the carbon cycle. We're not looking at what's happening with oxygen. This is just to see how far we can get with a relatively simple description. So coming back to the case study, you can see maybe at the top here is a relatively simple geology. There's a profile up the top here. We have a sandy soil underneath, and we have a peat layer at the top from the river system. So that's fairly straightforward. In modeling this, and the gray area you're looking at in the middle is the actual wetland area that we're interested in, then we have actually developed a number of different models. There's a model for the whole of the basin here. We have developed a smaller model around this wetland to provide boundary conditions, and then we've zoomed in finally to this wetland area, and we've been using the capabilities of MikeShe to just use boundary conditions from larger models to drive the local models. A couple of other things to notice in this figure is that we have some different profiles. The ABC, these are groundwater profiles, so there are piezometers on these profiles where we can look at the groundwater gradients, and then the small dots right close to these are actually where we have surface water measurements and profiles for sediment and for water level. We have a lot of information, fortunately, at least on the current state, and that includes also some water quality information. So we started out modeling, of course, the hydrology and the hydraulic behavior, and this is just a snapshot showing the inundation from in this wetland as in the current state from a wet period during January 2011. So what you can see is a couple of things, is that during these high flow periods, then the meanders are shortcutted by the flow. If we look at the main area of the wetland, you can see that the water is not just spilling into the wetland, it's actually spilling upstream and then flowing into the wetland upstream as well. So we also have some occasional measurements within that wetland area, and luckily some of them close to some of the larger events. And that's what the red dot is showing here. We can see that we seem to hit that fairly well with the model. If we look at the end of this time series plot on the right, you can see there's also a green dot, which we slightly underestimate. and that's kind of a pattern we've seen with all of the different measurements we have within the wetland, that it's a reasonable agreement, but some of the higher water levels that we're getting from the model are underestimated when we compare them with the measured water levels. But I think a reasonably good description here. And then if we look at the groundwater levels, here you can see the groundwater profiles again, A, B, C. And what we're looking at here is the time series from different piezometers along the transect A. The red dots show the observed groundwater levels, and the 2 lines show the water levels that we're predicting in the sand layer and in the peat layer. And we seem to get those levels quite nicely, and also some of the dynamics, even though we have relatively limited information about the dynamics in the time series data. And this is just to kind of summarize what we're seeing here and what that means for the flow patterns. So if we start at the top, we're looking at a winter flood, and you can see that the water levels are high in the groundwater. They're also high in the river system, shown by the cross right on the edge. And we're getting this behavior of water flowing from the river into the wetland and into the peat. But we still have coming from right to left a groundwater gradient. Then if we go down to the dry conditions in May, then we have gradients basically from right to left in both systems, and draining of the peat. And then again back in the summer, when we have in August, when we managed to get a lot of rains here in Denmark, a lot of rain, sorry, then we also have summer flooding. So we can see there's an interesting dynamic situation here. So having developed the model, and we're fairly happy with the results from that, then we wanted to turn back in time, and unfortunately we don't have a lot of information about the behavior of the river system, but we do have some information about the river prior to restoration. So if you're looking at this from left to right, what we can see is we can look at the hydro periods. These are some of the ecological indicators that you would want to look at in wetland areas. So on the left-hand side, you can see the very straight blue line. That's the unrestored system, or the heavily drained modified system. And you can see relatively short flooding periods, and then quite a dramatic change when we introduce these restoration measures on the right. And we can do the same kind of analysis for flood frequencies. Again, pre-restoration, relatively few floods, and then post-restoration, quite frequent flooding in this area. So the wetlands behaving as it should. And we also looked at the nitrate processes modeling, as I showed earlier, and there's a lot going on here. So let me kind of just take you quietly through this. The first thing to note really is that on the right, we have the pre-restoration case. So these are the nitrate behaviors in kilograms per hectare per year. And then in the middle, we have different cases of post-restoration. But I think just focus on the left-hand side where we have the reference case. And then we have different components of what's happening in the system. So the first thing to notice is that if we compare the red area, the red text, then we have pre-restoration, very low denitrification rates. And then thanks to the overland flow occurring on the wetland, we have a quite significant reduction in the nitrate. If we look at the yellow text, what we can see is that there is some nitrogen coming from the groundwater. There's a farming area very close by, which is also providing a lot of nitrate. But I should mention that most of the nitrate coming into the wetland is coming upstream through the river system, and therefore we're using the wetland to retain that. And then if we look at the behavior of in the saturated zone, so the SZ in this table here, we can see that we're getting some reduction here, and we're getting slightly more reduction here in the case of the restoration, but there's not a big change here. And then the other thing to notice is that we are getting a lot more, if we look down at the very bottom here, that we're getting a lot more nitrogen entering into the sand aquifer when we have the drain conditions, and that's makes sense. We're having water passing through the aquifer, so we're actually getting a lot of reduction from the groundwater through the groundwater system in that case. But but with the restored state, we're also getting a lot of reduction as well. It's not so significant here. So this is just a kind of a picture. On the left, you can see the profile that we're looking through here in the model and the piezometers here. And what you're looking at here is the groundwater plume of the nitrates coming from these agricultural fields that I've shown on the right, and how that's changing dynamically through the year. And you can see that what's happening is a lot of this agricultural drainage into the groundwater is either being lost into the peat, or else it's being lost into the river system and being reduced, diluted on the way through here. We also have some measurements of the nitrate plume along there, and quite reasonable agreement with the behavior of the model in the groundwater. So just to summarize, I think we have a nice model of what's happening in the hydrology and the nitrate processes, and we're finding that we get reductions or removals of about 130 to 150 kilograms per hectare per year, and that fits quite well with other empirical evidence that we have. Of course, it's the flooding and the denitrification in the wetland that's taking up most of that, and that was the purpose of this. And I think that is interesting. And I also think it's interesting that we could manage to model these different processes within the wetland area. If you want some further information, then I can refer to this conference paper, and there's also a journal paper in preparation. And you can contact me on this. So that was the first case, and let me just move on into the second case, which is a little bit closer to home for you guys. So can you see I hope you can see the next version. This is a case study that is kind of at the opposite end of the scales. It's a piece of work that we've done together here at DHI with some very good colleagues that I should like to acknowledge. And the point of this work is really not to look at developing a representative model, but more to investigate some of the uncertainties associated with modeling of riparian wetlands, and maybe some of the uncertainties that are usually not considered. And I like to start with this video because it reminds me a little bit that we need to think a lot about the uncertainties very often when we're doing this kind of flood mapping. This is an example of a historical flooding event in Boulder in Colorado. You can see the big blue area that is at the bottom here that is covered with some water is actually the designated floodplain. But what you can also see is in the areas in the middle on the top right, these are areas that were developed assuming that they would be well protected by the floodplain and the flooding pattern, but instead we got a very complex flooding pattern driven by the topography and by the road network. And I've just listed some of the sources of uncertainty here. And the typical ones we can envisage are the boundary conditions, the data that we're using, observations, and so on. But one of the things I wanted to look at in this study was what we call model structure. And an example of that you can see maybe here on the right. This is from the UK, and here it seems reasonable that we could probably model the flooding behavior of this river. This is Shrewsbury in the UK. We could probably model this with a one-dimensional model, whereas if we go back to the Colorado case, then obviously we would have to use full two-dimensional modeling. And one of the challenges we have is that on the one hand, we want to avoid these damages and the risks that are associated, and the risks and the costs that are associated with flooding on the one hand, and then on the other hand, we need flooding to maintain the health and the functioning of these wetland areas that we're interested in. And there's obviously a conflict between those land uses. And probably here you can get an idea that I'm going to be talking about an Australian case study. And one of the other things I think that is a challenge in this type of work is that, and it's a challenge we have with all types of modeling, is when do we have a good model? When do we know it's right? And especially in terms of flood inundation modeling, then we don't necessarily have a lot of information about where the flood has been and so on. So what we wanted to do is look into that as well, and we have in this case access to some satellite imagery and some aerial photography that we could also use. So this is the case study area, which I probably don't need to explain very much to the Australian audience, but this is the Murrumbidgee River, and that's a tributary to the Murray. And of course, it's heavily regulated, and there are wetlands, and there have been a number of wetlands previously. And you can get some idea of it in this video here. And this is further upstream, looking close to the river. And again, maybe in this case, you could model this area using a one-dimensional approach. But if you look to your right at these types of flood runners that give this very complicated flooding pattern, you can see that maybe we need to look at a combination of 1- and 2-dimensional modeling here. So this is the study area, which is a part of this area. And for those of you who know this, then you can maybe recognize parts of the area here. But this is just really for information and to show that we have some very clear boundary conditions for this area. And what we're looking at is these floods at the end of 2010 and 2011, and again after 10 years of not so much rainfall in Australia. We have a few pieces of information available to look at what is happening. We have some Landsat 30-meter resolution satellite data. We have some DIMOS 22-meter resolution data at a number of times. And we also have a single aerial image here around Hay down to quite a high resolution for December 2010. And that's the starting point for our modeling. And again, we're using Mike Shee to model this in the first instance, and we're using basically all of the components there. And what you're seeing on the right is the fact that we have, there's been flown LiDAR data for a large part of this area, which is very nice, but not the complete model area. So we've complemented that with some more large-scale topography. And that's one of the first things I wanted to look at. So this is just to show the flood extent at 3 different times. So the 24th of Christmas Eve, then the 28th, and then the 3rd of January 2011. And what you're looking at is in the background is the satellite optical images for those areas, and the dark areas are obviously showing areas that are wet. I should say they're not necessarily flooded. And that's one of the challenges we have with interpreting these optical satellite images. They may just be, the soil may just be damp. And if we just use the large-scale topography and model this area, then we get a flooding pattern that looks not much like the actual flooding pattern. And the reason I show this is because it makes quite some difference then if you then include the LiDAR, and then we can get quite good representation of the flooding patterns. Again, this is between Christmas and New Year in the satellite image, and then in the aerial image, we can see that, as expected, we get this full coverage, and that's because we have these protective banks around Hay here. So we've modeled this using Mike Shee, and again, this is using the Mike Shee model with a simple hydrological description, and then what we were interested in here is not just how well it compares with the satellite data and where we're capturing the flooding behavior, both upstream in the river system, but also downstream in this kind of large-scale wetland area. But also then looked at, how much difference does infiltration make to the modeling, and that's one of the first things that we looked at here. You can see that, as you might expect, by including infiltration effects, then we're actually reducing the flooded area, and of course that has some impact on if we want to use this for modeling the wetland behavior. And again, if we're looking at these kind of rapid urban floods where in the relatively small scale, then this is not necessarily important. But if we're looking at the wetland behavior on a longer scale, then how this water evaporates and drains actually affects the wetland ecosystem, and we'd like to know how much. So that was the work with Mike Shee. Then we said, well, okay, maybe some of the differences here are not just because of the modeling approach or the topography. Maybe we need to have a more comprehensive modeling approach for the flood dynamics. So we have been also modeling this with Mike Flood, which is you can see the comparison here. It's a hydraulic model, a fully hydraulic model. So we're solving the 2D fully dynamic equations, the St. Bernard equations, if you like. Mike Shee is a block-centered finite difference, whereas Mike Flood is a finite volume approach. Mike Shee has a more comprehensive description of the evapotranspiration and infiltration, but Mike Flood also has the ability to measure to include evaporation and infiltration, but doesn't include groundwater. And we just did a simple comparison here, again, basically using the same resolution and the same grid, using a square mesh, and you can see the blue areas here in which are the Mike Shee model, and then the yellow areas, the Mike Flood. And interestingly enough, quite different flooding patterns again in the wetland areas. And we suspect this is actually very small differences in the topography that make a large difference to the extent of the flooding, depending on how you map the spilling of the water onto the floodplain and the topography that's controlling that. And even more interesting, if we then use the triangular mesh to make very detailed modeling close to the river system, kind of contrary to our expectations, we found that this actually gave much more different flooding patterns. And again, the explanation of this is that if we look at in detail what's happening around the banks and around the river system, and have any uncertainties or errors in our water levels or in the topography, then they, in this very flat terrain, can make a huge difference to the flooding pattern. So I think this is an interesting challenge that we have. You can say that the nice thing here is we have the satellite imagery to compare and to maybe make a reality check on our modeling, and I think that's definitely the way forward for many of the pieces of work that we would like to do in inundation modeling. So this is just a kind of initial study, not to develop the perfect model, but to explore some of the things that could really impact what we're going to get if we try and model on a very large scale these kind of wetland areas. And part of that work will be that we need to go in and look more in the details about the topographical descriptions if we want to improve this. And then the question is, how do we do that in a systematic way? The other thing I think is interesting is that in the last 5 to 10 years, we have access to a lot more of satellite data. This is just one example taken from my colleagues here at DHI. At DHI GRASS, we have a satellite unit. And this is the very recent flooding in Myanmar. So 2009, and you can see here we have in dark blue, the permanent water, and light blue, the flooding pattern. And you can see we have a sequence of flood maps over here that tell us about what's happening on the very large scale in this area, and that again we can use to improve our flood inundation modeling at this kind of large scale area. So that was what I had for you today.